Hey, hi. Today I'm going to demonstrate how to set up a virtual shaker test simulation using Ansys. To understand the procedure, let's consider a simple problem. There is a 2 sheet metal bracket mounted on a product like automobile or ship or airplane. So this bracket is used to mount instrument which weighs around 50 kg, and there is a 5 washer used to connect the payload and the sheet metal bracket. The sheet metal bracket is made up of SAE 2310 steel. The product qualification test requirement is that we need to subject this bracket to a shaker table test, which is a typical 3-axis sine sweep test. The requirement is that we have to sweep 20 cycles from 10 to 200 heads in all the 3 axes. Okay, first sweep from 0 to 200 heads along the x-axis for 20 cycles, then do the same along y-axis, then do the same along z-axis. The vibration profile is given here. From 10 to 25 heads, it's 3 DA stands for double amplitude. From 25 to 75.5 G and 1.5 and 1 G on a higher frequency range. Again, for SAE 2301, typical material properties are given, something like Young's modulus, Poisson's ratio, ultimate tensile strength, and yield strength. So we want to set up a FEA simulation. Typically, one need to understand what is the objective of this simulation, or what's that we are expecting after doing the simulation. Typically, the objective would be to calculate the life of the bracket. Okay, so to qualify this product, we need to subject this product to this specific vibration test, and at the end of the test, we have to make sure the product is not going to fail, which can be accessed by doing a fatigue analysis. In order to do the fatigue analysis, we need the SN curve of the material as well. For this particular material, we have a SN curve also given with us. Another important thing to consider here is that the specification is not given consistently in terms of the acceleration or in terms of displacement. There is a mix of displacement and acceleration units. Because at low frequencies, the shaker arm can travel for a large distance, so it is easy to measure in terms of the displacement. But when we go at higher frequency, in order to meet this particular acceleration level at a higher frequency, the amount of displacement we may need is very minimal, so it is very difficult to measure that. So it's a common practice that at higher frequencies we specify vibration specification in terms of the acceleration. And also, it's important to understand what this dA means. If you have a typical sine vibration that representing the displacement, or this can be velocity or acceleration, anything. If we take from 0 or mean to peak, it's called a peak amplitude, or 0 to peak value, ZP. But if we take negative peak to positive peak, this is the total range, or also called as peak to peak or double amplitude, and so on. Okay, so again, there is no consistent terminology used here, so there is a mixed terminology. We have to see that. So in order to simulate this specification, we need to either convert all these peaks in terms of acceleration or displacement. But however, it's a common practice to convert all the specification in terms of the acceleration. So for a typical sine wave, once we know the displacement, that's u0 sine omega t, the velocity is nothing but the derivative of displacement with respect to time. So this will become omega naught omega u naught sine omega t. The omega is nothing but the circular frequency that in radians per hertz, which is nothing but 2 pi f. Okay. So again, for acceleration, if we take a derivative of velocity with respect to time, we get acceleration. That's nothing but minus omega squared u naught sine omega t. But the amplitude of this term is nothing but omega square u naught. Okay. So once we know this stuff, we know the displacement from 10 to 25 hertz. You can split that into small pieces, 10, 15, 20 and so on. If required, you can go at very finer frequencies, something like 10, 11, 12 and so on, if you have a lot of natural frequency mode shape within that range here. Okay. So once you know that, then we can calculate the acceleration amplitude. That is nothing but displacement and 2 pi f. F is nothing but this and f square. The 3 mm is nothing but double amplitude or peak to peak, so we need to take only half of that, such that this becomes acceleration amplitude. Okay. We can do like this for all the frequencies. Here, if you look at that, another complication is it ends at 25 and also this starts at 25. So there cannot be a two different vibration level at same frequency. So in order to accommodate that, give little increment, and this is nothing but 0.5 g. So we are going to solve this problem in mm square, in mm units. So the 1 g corresponds to the earth gravity in terms of 9810. If you are dealing with meter units, it will be 9.81 and so on. So this is a kind of a flat region, so straight away you can go between 25 to 75, because Ansys is going to interpolate for any frequencies in between. In the flat region, if we interpolate, it will be the same value. Again, starting from 75 to 110, it's again amplitude which need to be converted. Again, take a small margin. That's nothing but 0.15 by 2 pi f. That's omega square. This continues up to 100 hertz. Sorry, the specification is wrong. It is 100 here and 100 and here. Okay. So again 101.5 g. Sorry, it's 1 g, so 1 into 9.81. I hope I had used 0.5 g. Okay. So it's again good to just understand what is the g level at the lower frequency range. Okay. So this goes up to 3 g at around 25 hertz. Okay. This just for the understanding purpose. Having this done, now we have frequency versus consistent acceleration table. Now the first thing is to calculate something like frequency versus stress level stuff. Okay. So in order to do that, first I have the geometry here, and it's always a good practice to do a model analysis and understand what's the frequency range and so on. Okay. So when I do the model analysis, my lowest frequency is 25 and highest goes up to 209 and so on. Let's look at the modeling aspects of this thing, and here is the bracket. This is that thick washer which is of 5 mm, and other one is the bracket which is of 2 mm. And the 50 kg payload is considered as a distributed mass here on this particular geometry. That's where this whole the whole instrument panel is sitting on it. Okay. So there may be a different modeling strategies, creating a lumped mass at the CG location, considering both the mass as well as mass moment of inertia that may introduce some torsional modes and so on. But however, my objective here is not to discuss about the better modeling strategy to predict the natural frequency. So as a simplified approach, I'm considering this as a distributed mass. these edges are fixed as shown here. Then model analysis carried out, and you can understand the first one is the 25 Hz, and this is in the vertical direction. So what it means is that when we excite the structure in this one, so this will be experiencing 0.5 G and so on. Okay. Then also do a static analysis with unit gravity load to understand how much stress and deformation is happening due to the self height. This just for having a gut feeling. Okay, when there is no dynamic excitation due to the static self weight itself, the 45 MPa stress develops. Then set up 3 harmonic analysis. I'm doing a model superposition harmonic analysis, one for x direction, one for y direction, one for g direction. Fortunately, in this case, the sweep vibration profile is same in all the directions. There may be some other test specification where the different profile will be used in different direction. Okay. So once this is done, so what we are going to do is that in analysis settings, I'm going to use a logarithmic frequency spacing because I assume okay, given here we are going to do a logarithmic sine sweep, rather linear sine sweep. So I'm also using the logarithmic spacing between 0 to 20 Hz. So in order to capture the peak stresses near the resonance, I'm using clustering option, yes, and with 100 clustering points, which is a model superposition analysis. Then the excitation itself is applied as a global acceleration here. Acceleration level. So this is the component direction. This is components. By default it's vector change to components. Now you can copy paste this data here. Okay, so we have frequency versus acceleration data here. You can copy paste that. For x direction you can see its frequency x direction, in y jet it is 0. You can also see this arrow mark. Similarly, when you come to y direction, the analysis setting remains same, but the excitation is given in the y direction, keeping x and jet 0. Same thing in the g direction, x, y and y kept 0, and g direction the excitation is given here. Okay. And also it's important to consider the damping. I assumed a typical value of 5% damping. This is very important. Otherwise at the resonance point, you will see the stress amplitude going very high. Okay. So having this done, now we can after solving this, we can insert the frequency response curve for stress as well as for displacement. While selecting, you can select the entire model as the thing and use maximum to get the overall feeling for that. If you want to understand the maximum stresses at every point over all the frequencies, you can change. You can insert a principal stress plot like this, stress max principal stress plot, and change the type by maximum over frequency and amplitude. This is the maximum stress. So have a feel for the maximum stress in the x-axis excitation. It is 363. Look at y. This is around 510. Look at this. Look at these material data. No, it's even UTS. It's even going beyond the UTS. This is going to be a problem. This one. This is 510. This is the stress range. Stress range is the peak to peak. Okay, but what we are seeing here is nothing but 0 to peak. So 510 multiplied by 2, it's around 120. This in this case, the value is going to be somewhere, what is that, so 120, it's going to cause no, within few cycles it's going to fail. I expect this is going to be a 100 and 1020 somewhere here. I think within thousands of cycle it's going to fail. It's going to be a problem. Let's see how this goes. Okay, and the jet direction. What is important to notice here is that when we do the stress analysis, the things like 20 sine sweep, the 20 sweep, we can't do anything about this 20 sweep here. The 20 sweep plays a role in predicting the stresses. Okay, say for example, when we do when we see something like say for example max principal stress 510 MPa, what this means in the sense, this means that with respect to time, this is going to repeat like this. Okay, so this is 510 plus 510, and same way minus 510. This is going to repeat those many number of cycles, and this is going to cause fatigue failure. Okay, if this is a one single frequency, you can easily calculate how many cycles are going to happen, then compare with SN curve like this, and you can calculate the damage straight away. But here we are sweeping over the frequencies. It is very difficult to calculate the accumulated damage. So we are going to use the fatigue tool, wherein we will exactly be using the 20 cycles and x direction, y direction, and g direction, and so on. Okay, we will having this done, we will discuss how to calculate the life, or how to say whether this test is going to pass or fail after carrying out a detailed fatigue analysis studies. Having done the harmonic analysis, the next step is to carry out the fatigue analysis. For fatigue analysis, we are going to use Ansys nCode Design Life product. When you have appropriate licenses, you will see nCode analysis system appear here. For this analysis, we are going to use nCode SN vibration at Design Life. Drag and drop this on any one of the harmonic analysis systems solution cell, so I do here. Then we need to link all the three harmonic analysis system solution cell to the encode analysis system. By this way, it will read the result file generated from these three harmonic analysis. Having done this, then edit this. This will open up the encode file system. This is how it's going to look. The first thing I would recommend to do is that select all the system by pressing Ctrl A and move it right by certain amount. And the next thing I would recommend you to do is that by default this would expect the material properties required for fatigue analysis to come from workbench engineering data, but in this case we have not defined any SN curve for fatigue analysis in workbench material data, so we are going to delete this. Now by default it's linked with the analysis engine. Right click on advanced edit and say do you want to run the current flow up to this glyph so that sensitive data editing can be performed. So what does it mean in the sense, do you want to read the data from all the previous upstream glyphs before you do this edit operation? Say no at this time. By default it would, this is the one which is expecting the material data from workbench. Just say delete. Okay, don't use this. Moment you say delete, you would see this link disappearing here. Okay. Say okay, so this link is gone and you can delete this glyph also. We will later define the material data within nCode. So by default it has read three RST files from workbench. Just say okay here. The next job is to define the sine sweep profile. This is the vibration generated. Double click on this. By default this is going to be a random vibration analysis setup, so we need to change this to a sine sweep. You would see two sine sweeps. This one is kind of a old analysis procedure, so what is recommended to use sine sweep 2. Once you change this to sine sweep 2, it would ask for additional inputs. In this case we are starting from 10 heads to 200 heads, and we are going to sweep with one increment. If the range is little large, you can use the frequency increment little large, like 1 hertz is kind of appropriate here. If you are working in a very small range, then you can reduce this frequency step size. The another important thing is that sweep type, we are going to do octave per minute, and sweep rate is 1 octave per minute, and we can use the log interpolation method, and the test type is G here. Okay. Another important parameter we need to consider is the test duration. So we need to provide how much time it is going to take to do one sweep. Okay. That can be calculated using simple formulas. We have seen that in the past. How do we calculate frequency versus acceleration? There are formulas exist in the standard textbooks that relate sweep rate with the frequency range. So in this case our starting frequency is 10 Hz and ending frequency is 200 Hz, and the sweep rate is 1 octave per minute. Then using this particular formula we can calculate the number of octaves within 10 to 200 Hz. It's using formula ln of ending frequency by starting frequency by ln 2. We have around 4.3 octaves. Then next step is to calculate how much time it's going to take to do one sweep. Again we can use the same formula, ln f2 by f1 divided by sweep rate times ln 2. Since we are sweeping at 1 octave per minute, to sweep 4.3 octaves we are going to take 4.3 minutes. Multiply this by 60, so that it's going to take around 260 seconds for one sweep. Okay. That's the data we need to provide here. 260 seconds. This should be in seconds. Okay, that's what we are going to take. The next thing is that once we are done, we have to fill in this data by adding rows here. In our example, we have around 14 data points. We may add these 14 data points one by one and manually enter here. Instead of that, what we can do is that this vibration table, instead of property tab, we can use input pipe, so that you notice here where my cursor is, you can see additional connecting point appearing here. Okay, so just when you say additional connecting point, then from basic input we can create multi-column input glyph here. Then we can connect these two. In this glyph we are going to refer external file which contains this table. The external file will look something, so we are going to use a CSV file. The syntax would be something like this. Okay, sine sweep acceleration, frequency comma acceleration. The first, it will contain two columns. The first column represents the frequency and second column represents the acceleration. Units, the first column is of Hertz unit and the second column is of G unit. we can then copy paste this data. I just delete it. And also one need to take care of what sweep profile we are feeding into Ansys. There are two ways commonly followed. The one way is that we apply a unit acceleration during the stress analysis stage. Then whatever sweep table that we feed in nCode is used to scale this FRF, frequency versus stress curve, as per this table. Okay, so when we have applied a unit acceleration, that's the right way. In this case, what we have done is that during the stress calculation we have applied the actual acceleration, so there is no need to scale the FRF that we are getting from Ansys Mechanical inside nCode. So what we need to do is that there is no need to feed in exactly this data inside Ansys, but instead of that we have to feed in unit values everywhere, so that no scaling will be done inside nCode for the stress values coming from Ansys during fatigue calculation. Types are going to be float type. So we have this data available now. Just copy paste it here. It needs to be a comma separated, so just replace these white spaces by comma, replace all. Now this data is available here, okay, in D sine sweep, and copy this data. By default, when we drag and drop nCode, it's going to generate additional folder automatically inside Ansys. What we are going to do is that double click on that, odd data. So this is the folder wherein we need to put the data. So what we are going to do is that we are going to copy paste this data, the CSV file whatever we have created, to this folder. Okay, once we come and say scan, this file will appear, okay, because this file is inside this particular folder, or you can just browse to any location wherein you kept this CSV file. Okay, so just pass on this data here. say okay. I don't think we need to do anything here. This is done now. Rename this as fixed vibration generator. Duplicate this 2 times for Y and Z direction. Rename them appropriately, like Y vibration generator and Z vibration generator. By default, the original vibration generator has a histogram pipe connection with the analysis engine. For these two, we need to bring in additional pipe connection. Okay, so go to advanced edit, say yes. Now we can see only one histogram pipe exists. Add 2 more histogram pipe for Y direction and the histogram pipe for G direction. So rename them again for convenience purpose. It's histogram pipe and Y histogram pipe and G histogram pipe. You can see 3 additional pipe connections appearing here like this. Connect them. Then edit load mapping. Yes, so we need all the FRF and something coming in. Okay, it says there is no profile to these 2 providers. Okay, we need to connect this. um, in this case we have the same sweep profile for both x, y and z direction. There may be cases where the sweep profile will be different for x, y and z direction. In such a case you have to bring in 3 multi-column input glyph and connect with the vibration generator. So not this edit load mapping, yes. So we have three FRF, which is nothing but the harmonic analysis stress results, frequency versus stresses. We need to define a duty cycle to take care of sweeping in all the 3 directions. So vibration load provider 3 times for x, y and z direction. Name them appropriately. X sweep, rename this as y sweep and this as g sweep. Okay, so once these are all the 3 events part of this duty cycle. Now we have to map this is x-axis FRF should be mapped with the x profile. Say okay. Similarly for y, it has to be mapped with y profile. G, it has to be mapped with G profile. Just drag and drop here. Okay. These are all the 3 steps, and another step is that the loading configuration, we don't want to define it again. We can say this is coming from metadata, such that what would happen is that instead of defining it again, it will straight away pick it from the vibration generator. Okay. So this need to be set for all the things x, y, z direction, metadata, jet sweep, advanced metadata. This is done. The another important factor is the repeat counts. In our problem definition, it's shown that there is a 20 sine sweep. Okay, so 10 up and 10 down. Up means going from 20 hertz to 10 hertz to 200 hertz. Down means coming up from 200 hertz to 10 hertz. In reality, if there is any bolted connections or weld, due to some kind of a non-linearity, we may see the difference between sweeping up and sweeping down. But in the analysis world, harmonic analysis being a linear analysis, we can't capture any of the non-linear effect. So the result will be same when we sweep up or sweep down. So eventually the total sweep is 20 sweeps. It's 20 sweeps in all the 3 directions. So we need to provide 20 here, 20 here, and 20 here. In case for some other test requirement, the number of sweeps in different directions are different, you can specify them. The next item is to set up the material definition for these. So to assign material properties, say edit load mapping and say yes, update all the data. Now what we need to do is that these are all the different materials we are going to use. If you are having a complex model, you can identify what material 1 corresponds to, what material 2 corresponds to, and so on. We are going to use the standard SN curve because we are not going to use multiple R ratio SN curve. So change this to a standard SN curve. Now we need to add a library where this is available. By default, nCode provides a material library which is available here. If you go to Ansys installation directory, nCode and design life glyphworks, and inside that there is a folder called mats. Okay, inside that there are different material libraries available. We are going to browse to this file and we are going to use nCode material library here. We can see multiple materials defined in this library. what we are going to use is SAE 2310. Let's scroll down and see SAE 2310. Can just view the properties, and you can also have a look at the SN curve. One important thing to understand here is the y-axis given in the range instead of amplitude. Okay, it's important to understand this difference because what range means 0 to peak. The amplitude means 0 to peak. The range means peak to peak. Okay, so whatever the stresses that we see in Ansys harmonic analysis is 0 to peak. It's amplitude value, not the range value. So that's something you need to keep in mind when you are looking at the material data. Okay, so once this is done, and select all these and click this up arrow, so all the materials assigned with this particular property. Now we have material definition assigned. Advanced edit, analysis engine. We want to use standard SN curve, and there is only single one SN curve, so we can't interpolate. Typically you may use a Goodman diagram if there is any static offset. If there is no static offset, eventually you can go with none. The another thing is that we want output for every event, like that, so that we can understand how much damage is caused during X direction sweep, how much is during Y direction sweep, and how much during G direction sweep, in addition to the total damage. The same thing need to be set for both the analysis engines, and also we will use max principal stress based fatigue calculation. Output event results true. To view the individual event damages, we have to also set event per channel true here. Once this is done, the last setting is that we have to make sure the unit systems are correct. We have solved the harmonic analysis in Ansys Mechanical using MPa unit system. So this has to be in MPa, tons and Newton meter. If you see this in some other unit, make sure you set this in MPa, tons, and so on. Having this set, I think we are through to run. We can run the model. So it's going to run two scenarios. One is the first cut course analysis, and the second one would be a detailed analysis. So once the analysis is done, by default you will see the results. If you click here to make this big, if you double click here, this is the damage due to X, Y, Z sweep, and this is the overall damage. Let's look at the overall damage. Life. See, the life is only 0.65 duty cycle, or in other words, when you look at the damage, the damage is more than 1. It means that it is going to fail. We cannot do 20 sweeps in X direction, Y direction, and G direction. It's going to fail before that. Okay, this is the overall life. If it is going to meet the 20 sweeps in X, Y, and Z direction, then we will see minimum as something like 1. Now let's understand which excitation is causing more damage, or let's see the life. Okay, when we do a sweep in the X direction, okay, we are seeing 4203. What does mean in the sense? So it is 20 into 4203 sweeps, or in other words, one test is 20 cycles, in the x direction we can repeat 20 blocks of 4203. Okay, so the x direction excitation is not causing much problem. Let's look at y direction. So y direction sweep, oh okay, this is causing the major problem here. Okay, this is 0.65. It means that what it means is that we have 20 sweep is one block, it's nothing but 0.65. okay, so it can withstand only 13 sweeps in the y direction. It can't withstand, so it really calls for some design changes and so on. Let's look at g direction. G direction is also very large number of cycles. Okay, it is something like 40,000 cycles. It's not a problem. So y direction is what really calling for the damage and things like that. We can go and look at this y direction stress response as well. You can see that. Okay, so when we exert this in the y direction, we are seeing a very high stresses developed in the model. Okay. So the max principal stress, let's see, max principal stress maximum over frequency. Yes, we need amplitude. If you see that, yeah, it's coming around 500 here. Okay, this is causing the most damage. If you look at again here, this is happening in the first mode. Probably let's see what's the first mode from the modal analysis. The first mode is something like this. Let's set some auto scale. Yeah, so this is the y direction mode. This is causing some problem. Probably we have to add some stiffener and all to make sure this product passes this particular test requirement. Okay, so in summary, to address shaker table vibration simulation problem statement, something like this, we need Ansys Mechanical to calculate the stress over the frequency, and we need nCode to calculate the damage and life due to the vibration excitation requirement. The point to remember here is that for the stress calculation purpose, only the frequency range and vibration levels are used. The information about number of sweeps and the type of sweep, sweep rate are nowhere used. These are all the parameters required to calculate the fatigue lag. So they are really not useful in the harmonic analysis as such, but however they are very much required to calculate the fatigue life of the product. Okay, I hope this video gives you some guidelines on how to do a virtual shaker vibration test qualification using Ansys. However, the material data and the stress numbers or the model that you are seeing in this example are just for the demonstration purpose. The number itself may not make any physical meaning. This is only for the demonstration purpose. Okay, thank you.